This is an example of hypothesis testing for a mean when sigma, the population standard deviation, is unknown. So in our example, Planet Fitness Inc. has determined that the average amount of time that clients spend at the gym is 48 minutes per visit. They recently opened a new location in Adams and want to determine whether the average amount of time spent is different than their overall average across the country. They will test this claim with an alpha equals 0.01 level of significance. They randomly select 60 clients and find that the average visit is 45.2 minutes with a standard deviation of 7.3 minutes for this sample of size 60. So I'd like you to try this out. Grab some paper and pencil. So is this a one-tailed test or a two-tailed test? Write the null and alternative hypothesis. Determine whether or not to reject the null hypothesis by finding a confidence interval for the mean, assuming that the null hypothesis is true. And in both parts 2 and 3, explain the result in context. So do pause and try this out. Okay, so first of all, is this a one or a two-tailed test? This is a two-tailed test because we were specifically looking to see is it a different amount of time spent on average than their overall average across the country? So they're not saying, is it larger, is it smaller? They're saying just, is it different in either direction? So it's a two-tailed test because the direction is not specified. And the null hypothesis, H naught, is that the mean for this Adams location is still 48 minutes. The alternative hypothesis, H sub A or H sub 1, is that the mean is not equal to 48 minutes, that the mean is different in either direction. Next, we want to determine whether or not to reject the null hypothesis by finding the test statistic and comparing it with the critical value from the t-distribution. So here, we are going to use t equals the sample mean minus the mean from the null hypothesis, the mean for the population, divided by the standard deviation of the sample over the square root of the sample size. So from the problem above, we have that the population mean is 48 minutes from the null hypothesis. The sample mean is 45.2 minutes. The sample standard deviation was 7.3 minutes. The sample size, 60, is n. And, one other piece we have here is alpha, the level of significance, which we will use. Okay, so we can plug some of these values in to get our test statistic t. Again, that's the sample mean minus the population mean divided by the sample standard deviation over the square root of the sample size. And that gives us a value of negative 2.97. So that's our test statistic based on the sample, t equals negative 2.97. We now find the critical value from the t-distribution. The critical value is the value that tells us when do we reject the null hypothesis. So using the t-distribution, we need two pieces. We need to know what's the area in the tail, in one tail, and what's the degrees of freedom. So this is a two-tailed test where alpha was 0.01. We want to be thinking about the probability of an extreme result in either direction. So instead of using 0.01 for our column, we're going to use half of that, 0.005, because if the total probability of an extreme result is 0.01, the probability that will be in each tail is 0.05, half of that in each tail, half of 0.01 in each tail. Okay, so we use the column 0.05 in the t-distribution, and our degrees of freedom is the sample size minus 1. Our sample size was 60, so 60 minus 1 is 59. 59 is not explicitly in the table. It doesn't really matter too much which one you use. A conservative estimate would be to use the smaller of the two values, row 50. Some people also find an average. If you use 60, that would be okay too. These are very small differences when you get to this point in the table. So we'll use row 50, column 0.005, and that gives us a critical value of 2.678. So 2.678 is our critical value. And what that means is this gives us the critical region if we were either above 2.678 or below the opposite, below negative 2.678. If we're in either tail, then we reject the null hypothesis. And if we're in the middle, then we are not in the rejection region. We do not reject the null hypothesis. So in our case, because the test statistic, negative 2.97 that we first calculated, is in one of the tails, we do reject the null hypothesis. This means that we have enough evidence to say that the atom's location has a different average visit time than 48 minutes, the average visit time across the country or at all locations. Okay, now let's do it in the other manner of doing it, the confidence interval. So we'll start by finding a confidence interval for the mean, assuming that the null hypothesis is true. So our confidence interval for a mean is the mean minus a margin of error to the mean plus the margin of error, where the margin of error is t times the sample standard deviation divided by the square root of the sample size. These are the values from reading the problem above. Population mean according to the null hypothesis, 48 minutes. Mean from this sample, 45.2 minutes. Sample standard deviation, 7.3. Sample size, 60. And our level of significance was 0.01. So we're going to get t from the t distribution just like we did above in part 2. So we use the table with area in one tail is 0.005 and degrees of freedom is 60 minus 1 is 59. Using the row degrees of freedom equals 50 gives us a value of t equals 2.678. So that's our value for t. So that means our margin of error is t times the sample standard deviation divided by the sample size, square root of the sample size. And this gives us a margin of error of 2.52. So our mean minus our margin of error to our mean plus our margin of error, this is our confidence interval, is this, which gives us 45.48 to 50.52. And so now we say, okay, was our sample mean in that confidence interval? Our sample mean was 45.2, and that sample mean is not in the confidence interval. So our confidence interval goes from 45.48 to 50.52. If our sample mean had been in here, we would not be rejecting the null hypothesis. We would not have enough evidence to say that there is a difference. But our sample mean was in one of the tails. It was in the rejection region. And so we do reject the null hypothesis. In context, this means that we do not have enough evidence. In context, this means that we do have enough evidence to say that the atom's location has a different average visit time than 48 minutes, the average time at all locations. So our null hypothesis was that the average visit time is the same in atoms as it is everywhere else. We rejected that hypothesis and found that the average visit time is in fact different because we had a result whose probability was very small.